Welcome to this explainer from Forge College. I'm absolutely thrilled to have you here today. If you've been following along with this track, you know we've been tackling some incredibly fascinating, albeit pretty dense concepts in the Web3 space. Today, well, we're taking a massive leap. We're diving into BFT consensus algorithms and real-world applications. Basically, we're going to take those abstract blockchain trade-offs we've talked about and map them straight to the concrete real-world consensus algorithms that literally power the networks we use every single day.
So, in our previous lesson, evaluating BFT, comparisons and trade-offs, we spent a lot of time kind of hovering up in the theoretical clouds, right? We looked at that abstract tug-of-war between throughput, how much data a network can process, and finality, which is how quickly and permanently that data is actually settled. Well, today we are getting our hands dirty. We're moving away from those abstract ideas and getting right into the concrete engineering tools and deployment patterns used by real developers. We're going to look at the exact algorithm families you'd pull right off the shelf to build a production network.
Here's a quick rundown of our blueprint for today. First, we've got the switchyard metaphor. Second, the three BFT families. Third, a real-world blueprint. And we'll wrap it all up with our operational takeaways.
All right, let's jump right into part one, the switchyard metaphor.
To really wrap our heads around this, I want you to picture a bustling railroad switchyard. In this mental model, the incoming trains, those are our client transactions, the data just waiting to get onto the blockchain. The tracks they run on represent our communication channels. The physical switches that direct those trains into properly ordered tracks are our consensus logic. And the yardmaster, that's our consensus leader. This yardmaster has the absolutely crucial job of coordinating which train moves next so we don't have a catastrophic collision. As you can probably guess, if that all-important yardmaster falls asleep at the switch, the entire yard just comes to a grinding halt. So keep this image in your head as we move forward.
Which brings us to part two, the three BFT families. Let's meet the different types of yardmasters running these networks.
First up on the list, we have classical leader-based protocols. Think of protocols like PBFT here. This is basically your incredibly strict single yardmaster who insists on coordinating every single move. Seriously, before a train is allowed to budge even an inch, this yardmaster proposes a plan, radios every single switch operator on the network, and waits for them to explicitly confirm the plan. Only when every single person agrees does that train actually move.
So, what does this actually mean in practice? Well, the trade-offs are pretty clear-cut. Because of all those explicit prepare and commit votes, you get incredibly predictable latency and absolute safety. You know exactly when a block is final. But man, the overhead is heavy. It requires an exponential amount of messaging, which engineers call an O of n squared communication complexity. And the biggest risk here? If your single yardmaster goes offline or even just experiences a minor glitch, your entire network stalls out until a deputy yardmaster can step up and take over.
Moving right along, our second family is optimistic and pipeline protocols. Now, if our classical yardmaster was strict, these yardmasters are total adrenaline junkies. To speed things up, they pre-clear tracks and allow multiple operations to overlap speculatively. They tentatively accept proposals and just keep those trains moving, working under the assumption that everything will likely be fine and they can, just confirm the paperwork later.
The obvious benefit here is blindingly fast throughput under normal conditions. I mean, trains are literally flying through the yard. But here's the kind of terrifying downside. High throughput is amazing right up until two trains crash. When one of those speculative risks actually fails, you need these incredibly complex, resource-heavy switchbacks, or rollbacks, to reverse the whole speculative mess, clean off the tracks, and reorder all the transactions. Basically, you're trading absolute certainty for raw speed.
Our third and final family is leaderless or DAG-based protocols, and DAG just stands for Directed Acyclic Graph. For this one, I want you to imagine completely firing that single yardmaster. Instead, you have many small, independent switchyards that are all accepting trains concurrently. They process their own local traffic, and then they magically merge their schedules together after the fact to create one massive ordered ledger.
Now, this is the absolute pinnacle of parallel throughput, and it totally eliminates that single leader bottleneck we talked about earlier. It's also highly resilient to adversarial delays because, well, there's no single target for an attacker to hit. But of course, there's a catch. It comes at a massive engineering cost. You need these incredibly complex local merging rules. It's honestly like trying to flawlessly weave 10 completely different train schedules together on the fly without causing a single delay. The math and the logic required to mathematically prove everything is in the correct order are highly, highly intricate.
Okay, so here is your engineering spec sheet.
Let's summarize. Classical gives you moderate throughput with multi-round messaging, but it fails if the leader fails. Optimistic gives you high throughput speculatively, but it fails via those messy, complex rollbacks. And leaderless gives you very high concurrent throughput, but the failure surface there is the sheer complexity of the merging logic. Understanding this table is essentially the secret to reading any protocol's white paper and instantly knowing its operational weaknesses.
So let's put this into practice. Part 3, Real-World Blueprint.
Let's look at a real-world case study. Imagine you've just been hired to advise a consortium of major financial institutions. They're building a permissioned ledger for interbank settlement. They are demanding immediate, irrevocable settlement finality, meaning when $1 million moves, there is no way it can be rolled back. None. They also need predictable latency during business hours, and they want a 10-node network that can safely tolerate up to 2 faulty or hacked nodes. So, which yardmaster do you hire for the job?
Well, if you chose the strict yardmaster, you hit the nail right on the head. Here is step 1 of our blueprint. We match classical BFT to their finality needs. Banks simply cannot tolerate the speculative rollbacks of an optimistic protocol. It's a non-starter. Step 2, we set up a primary/replica topology, designating 1 leader node and 9 replicas validating its proposals. And step 3, because we know that primary node is a major bottleneck, we rigorously implement automated standby leader failovers.
Now, it's absolutely crucial that our math checks out here. Classical BFT relies on a specific formula. N must be strictly greater than 3F. N is the total number of nodes, and F is the number of faulty nodes. So our bank wants to tolerate 2 faulty nodes, right? 3 times 2 is 6. That means our total node count, N, must be greater than 6. Since the bank is deploying a 10-node network and 10 is definitely greater than 6, our fault tolerance math is perfectly viable. This network will remain completely secure even if 2 nodes go totally rogue. But listen, just deploying the algorithm isn't the end of the story. You actually have to keep it alive in the real world. Operationally, you've got to tune your failover timeouts extremely carefully. You definitely don't want to accidentally fire the yardmaster and trigger a massive view change just because of a tiny bit of network jitter, right? You need to monitor leader latency like a hawk. You also want to distribute your validators geographically across different data centers so local power outage doesn't take down the whole system. And finally, you use snapshot-based state catch-up. This way, if a node does crash, it can quickly download the latest state and jump right back into the action.
Which brings us to our final segment, Part 4, Operational Takeaways.
Let's distill all of this down. Rule number 1, choose classical BFT when your primary business constraint is strict, immediate finality. If you are dealing with high-value assets where a rollback would be catastrophic, like our banking example, you need that strict yardmaster. But just remember, getting that predictable latency and absolute finality means you need diligent leader failover planning and state catch-up mechanisms to mitigate your single point of failure.
Rule number 2. Choose DAG or pipeline designs when your network demands massive concurrent throughput and you want to avoid that single leader bottleneck. But, and this is a really big but, you must explicitly budget for the complexity. Immense speed comes with a heavy cost. You're going to be maintaining robust rollback procedures, intricate ordering logic, and highly specialized monitoring tools just to make sure your localized switch yards are actually merging correctly.
So I'm going to leave you with this provocative thought. We've seen exactly how these algorithms handle speed and finality. But how will your algorithmic choices govern the actual decentralization of your next network build? Does relying on a single yardmaster inherently centralize power, even in a distributed network? Well, that is exactly what we're going to tackle in our next lesson, Defining Decentralization in Blockchains. If you want to dive deeper into this and explore the incredible variety of courses we offer, I highly encourage you to visit forge.college to continue your learning journey in Web3. I'm your host, and until next time, keep exploring and keep building.